Okay, some more problems from the 2008 multiple choice. Okay, what are all the horizontal asymptotes of this graph in the xy plane? Now this is a tricky one. Now remember, in order to find horizontal asymptotes, we want to take the limit as x approaches infinity. Now remember, we can have some curves can have a horizontal asymptote as x goes to positive infinity. They can have a different one as x goes to negative infinity. All right. Sometimes you'll see a curve like this. And notice it has a one horizontal asymptote as x goes to negative infinity, and a different one as x goes to positive infinity, so make sure you check both limits. Now this is a tricky limit issue because we can't use L'Hopital's rule because exponential equations just keep regenerating themselves. E to the x is just e to the x, e to the x, and this is just going to give us 2 to the x times the natural log of x, and another 2 to the x times the natural log of x, or natural log of 2, 2 to the x, natural log of 2, 2 to the x, natural log of 2. We just keep getting, we can't get rid of anything. So you have to use an algebraic technique. Now if we take a look at this, as x approaches infinity, we want to get something, some way we want to get 0 and some denominators, so when x approaches infinity, we want to get the x, I think, this x term in denominator, so when x approaches infinity, then the fraction that is part of goes to 0, and that's real easy to, show that it disappears. All right? So this is what we're looking at here, this issue. So what we do is we just divide everything by 2 to the x. That's the only way we can handle this. So 5, if I divide 5 over 2 to the x, 2 to the x over 2 to the x, 1 over 2 to the x, and negative 2 to the x over 2 to the x. And what happens is this is just 1, and this is just 1, so we end up with this. 5 over 2 to the x plus 1, 1 over 2 to the x minus 1. Now, if I take the limit as x approaches infinity of 2 to the x, that becomes infinity. 5 over infinity is 0. 1 over infinity is 0, so those 0 out. So I just end up with 1 over negative 1, so the limit is negative 1. Okay? So take a look at that, because this is a kind of a specific type of problem there where you have to resort to these algebraic little techniques, because the AP people know now that you all know L'Hopital's rule. So they try to come up with these limit questions where you can't use L'Hopital's rule. You have to use some of the algebraic techniques, and this is one of those algebraic techniques. Now here comes the other part. What happens as x approaches negative infinity? All right? Well, we don't know what happens when we have 2 to the negative infinity. I know that 2 to the infinity becomes positive. But what's 2 to the negative infinity become? Does that become really, really small? Or does that become really, really big negative? That causes some issues. So we don't really want to deal with 2 to the negative infinity because we're not too sure. We know 2 to the infinity becomes big. But 2 to the negative, 1 over 2, we don't know what that does. So what we can do is we can change this to, we can take this and then put this in the bottom of a fraction. So we can make this as 1 over 2 to the negative x. And this would be 1 over 2 to the negative x. Now as x approaches negative infinity, what's a negative times a negative? This becomes a positive. So all I did was rewrote this as 1 over 2 to the negative x, but a negative, if I substitute negative infinity here, that negative times the negative becomes a positive, so I've got 1 over 2 to the infinity again. Same thing over here. So all I had to do was just put these in the bottom. I didn't have to divide everything. And if I do that, look what happens. This goes to 0, that goes to 0, so I have 5 over 1. So as I go to negative infinity, my asymptote is going to be 5. So it's going to look a little opposite. It's going to look opposite of what I wrote. All right. So if we take a look at it, it's going to look something more like this. There we go. As x approaches negative infinity, it's going to go to 5, towards 5. and x approaches positive infinity, it's going to go like towards -1, so it'd be something like this. This might be -1, and this might be 5, so it looks something like this. As x goes to negative infinity, and x goes towards positive infinity, it'll look something like that. Okay? Or that's one way it could look, okay? Okay, so that's a tricky one. It was so tricky that they actually didn't even count it in the grading. I guess so many students had trouble with it. For this, they only used 44 points rather than 45. So you had to change the factor. So that was a tricky one. Okay, so just be careful, because everybody knows the word is out, so they may give you another one on the new test, and they may want to say, well, did everybody kind of learn their lesson? And learn to check, because a lot of students didn't check both infinities. They probably just checked the positive infinity, and so many of them got it wrong that they just had to throw it out. But now everybody knows, so more people will get it right, so it may work again. So watch out for something like this, okay? Always check your limits as x approaches not only positive infinity but negative infinity, and try to remember how we do these little fractions. Okay, so that's number 19. Number 20. Okay, let f be a function with a second derivative given by f of f double prime equals x squared minus times x minus 3 times x minus 6. So this is the second derivative. What are the coordinates of the points of inflection? So we just want to know when that changes signs, SIGN. So we check the end behavior first, and this is 2, that's 1, and that's 1. So if we multiply these out, x squared x gives me x to the 4th. So notice my end behavior is my hands up. Okay? In other words, it's going that direction. So it's coming from here and then headed towards there. All right? And these were the zeros at x equals 0, x equals 3, x equals 6. So what happens at 0? Well, since that's even, it touches and returns. And at x equals -3, it's odd. That's the first power, so it crosses. And x equals 6, it's odd, so it crosses. So it looks something like that. Okay? So now if I look at this is just my second derivative, so that's my second derivative test, and I can check for points of inflection is where concavity changes. So here it's positive, here it's positive, here it's negative, and here it's positive, because it's going above the graph. So here's concave up, concave down, concave up. So I have 2 points of inflection. That's when concavity changes, 3 and 6. It stays plus here, but it goes from positive to negative, negative to positive at 3 and 6 only. So those were points of inflection. All right. And then number 21. Okay, a particle moves along a straight line. The graph of the particle's position at x sub t is the graph of the particle's position x sub t at time t is shown for 0 to 6. The graph has horizontal tangents at t equals 1 and t equals 5, and a point of inflection at t equals 2. So that's when concavity here changes from positive to negative. For what values is the velocity of the particle increasing? Okay, now basically the particle is moving here. As time goes this away, the particle goes down, then goes back up here, then up there, and then back like that. So that's what the particle is doing. So if you kind of visually follow that, it's going to go down here to there, stop, go back up here, go back up there, stop, and come down a little bit. Okay. Now remember velocity. So we want to know when is the velocity increasing. So velocity is increasing when the acceleration is positive. All right? The velocity is increasing when the acceleration is positive. Okay? Now this is my position function. All right? So we want to know when the acceleration is positive, so that's when the curve will be concave up. Okay? So it's concave up from 0 to 2. Then it's concave down from 2 to 6. All right? Now again, here my slope is negative, all right? Okay? But that just means that the velocity is negative. Here the velocity is positive. Here the velocity is negative, but we want to know when the velocity is increasing. So even though the velocity is negative, it may be slowing, getting not so much negative, so it may be increasing. If you're going at minus 45 miles per hour, then all of a sudden you're going at minus 20 miles per hour, then what's happening is your velocity is increasing. So that's basically why we look at the concavity, all right? All right? So even though the velocity may be negative, it's increasing. And now it's positive. Okay? And even though it's positive, it may be decreasing as far as it gets up to the slope, and then it slows down, and and then stops. All right? So this is actually where the particle stops. So my velocity is negative. All right? But it's way negative, and it's coming to zero, so that's what's happening. So you really have to look at this. So what we did was we just kind of looked at this, and we said it's concave from 0 to 2. It's concave up. So that means that the second derivative is positive, and then from 2 on, it's concave down. That means the second derivative is negative, which is, so that's the second derivative, and that's the acceleration. So here the acceleration is positive, here the acceleration is negative. When the acceleration is positive, the velocity is increasing. When the acceleration is negative, the velocity is decreasing. So I hope that makes sense. So you have to think about that one. Okay? Be careful that you don't confuse this as where the velocity of the particle is positive. All right? Here the velocity is positive because the slope is positive. All right? Here the velocity is negative. All right? Here the velocity is negative, but not increasing. All right? Here it's increasing, here it's decreasing because of the concavity. So make sure you think about the difference between those two concepts. The positive or negativeness of the velocity and where it's increasing or decreasing. Okay? Hope that helps.